On graded potentials aren't like action potentials because they occur in different places and they're not all or nothing, and they decrease in magnitude. So first of all, graded potentials are going to occur on the dendrites, which are the dendrites, recall, are the receptive region of neurons. Axons are the conducting regions of neurons, while dendrites are the receptive region. So that's important. And these graded potentials, that means that graded means they're going to decrease in magnitude with distance. Action potentials can go on forever. Graded potentials cannot. And what's going to determine how far these graded potentials go is how strong the initial stimulus is. If the initial stimulus is strong, then the graded potentials will travel further. And where these graded potentials are going to travel is towards their goal, is to get towards the axon hillock. Because if they get towards the axon hillock, if they get all the way to the axon hillock, what they're going to do is they're going to make an action potential born. They're going to create an action potential. So that's what we want, these graded potentials to reach the axon hillock. Graded potentials can either produce a depolarizing stimulus or a hyperpolarizing stimulus. They can be depolarizing or hyperpolarizing. So let's take a look at that on the graph. Where's my little graph? Where'd it go? Let's look at the graph first. So if we had a stimulus that was applied, and here we have resting membrane potential, this is what a depolarizing stimulus would do. It would cause the graph to look like this. This is depolarization. Remember, depolarization is when the membrane becomes less negative. It goes up like this, or more positive, same thing, like this. If we were to hyperpolarize the membrane, the hyperpolarization looks like this. We're becoming more negative, so we're going down like this. So a hyperpolarizing stimulus would do this. And what would be a hyperpolarizing stimulus? Would be a neurotransmitter that would do that, make it go down like this. What would be a depolarizing stimulus? Was a neurotransmitter would make it go like this. Da, da, da. All right, so let's go back to that slide that we missed. So again, graded potentials travel on dendrites, and important, they can also travel on cell bodies. That's another place that they can travel, but I'm focusing on the dendrites, and they fizzle out over distance. They just fizzle out. They can just out they go. And they can summate. Summate means to add. So they can summate temporally or spatially. So temporally means over time, and spatially means over distance. So I'll show you what these two guys mean in an upcoming picture. Temporally means, like I said, over time. If a graded potential goes bam, 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 bam in the same place, we can end up with a really strong current of electricity ending up at the axon hillock. And if it ends over space, if we have graded potentials arriving at a bunch of different dendrites, then all those dendrites can end up sending their graded potentials to the axon hillock, and we get the birth of an action potential. Oh, it's very happy. Okay, now we have two types of graded potentials. We have an inhibitory postsynaptic potential, and then we have excitatory postsynaptic potentials. Inhibitory, just as they sound, they are potentials that hyperpolarize the membrane. They drive us further away from, they're going to drive us further away from threshold. They're going to prevent us from causing an action potential at the axon hillock. And an excitatory postsynaptic potential, they're going to depolarize the membrane, and so they're going to depolarize the membrane at the dendrite, and so hopefully that will help us when this wave of electricity gets near the action potential. It will excite it to where we create an action potential on the axon hillock. So we can abbreviate this IPSP, IPSP, or EPSP, EPSP. That's what I like to do, IPSP and EPSP, as long as you can remember that. What they stand for, inhibitory postsynaptic potentials and excitatory postsynaptic potentials, and which does which. Inhibitory hyperpolarize and excitatory depolarize. They do this, by the way, the inhibitory postsynaptic potential, they does this, hyperpolarizes the membrane by opening up potassium or chloride channels, and the excitatory does this by opening up sodium and potassium channels. So this is just what it looks like. This is what, if the membrane right here, if we're at resting membrane potential, and at this spot right here, we were to excite the membrane and we were to depolarize it, this graded potential in this area would travel along and it would fizzle out. An action potential, if we were depolarizing the membrane up to this part, say this was positive 30 millivolts, this action potential would cruise along for however long the axon was, and it would stay up at this rate. But graded potentials, when they're traveling along a dendrite, it stimulates it in this one area, the original site of the stimulus right here, and then as it just fizzles out. And hopefully if it were to make it to the axon hillock about right here, maybe it would create an action potential, but maybe not. But it might fizzle out before it even gets to the axon hillock, because that's what they do. They just fizzle out. This is the same picture that you saw before. An excitatory postsynaptic potential depolarizes the membrane, but in this case, it's depolarizing it below threshold. So this excitatory postsynaptic potential, even if it did make it to the axon hillock, because it's not going to be above that 55 millivolts, it's not going to reach threshold, even if this, because this is an EPSP, this is considered a graded potential. If this graded potential makes it to the axon hillock, it is not going to create an action potential because it's a sub-threshold stimulus. It's just a little baby. It's not going to do anything. Now, if this is an inhibitory postsynaptic potential and it makes it to the axon hillock, it's definitely going to drive the axon hillock away from threshold. It's going to drive it farther away from threshold, and it's going to prevent that axon hillock from creating an action potential. Now this one might get the axon hillock a little more closer to threshold, so the next excitatory postsynaptic potential that comes along might get it, right there to it, but this alone is a subthreshold stimulus. So let's talk about summation. This is summation right here. Here we have, in this graph, we have no summation. We have a stimulus that's being applied to this membrane. Here we have the dendrites, because the dendrites are the receptive region of this neuron. And here's the axon of this neuron. Now, we have a synapse here. This is the axon coming into this cell. Because this is the axon, this is the conductive region for this cell. And this is the receptive region for this cell. And this is what we would call a synapse, right? So this cell, because the information is going from this cell to this cell, and this is the synapse, we would call this the presynaptic cell, and this is the postsynaptic cell, because information is flowing in this direction. Not because there's an arrow here, but because information has to flow in this direction, because axons are always taking information away from the cell body. And this is the axon, so this axon belongs to another neuron that's not drawn here. So information is going away from this axon. It has to be going to this axon. So this is our presynaptic cell because it's before the synapse. And here's our postsynaptic cell. So we have a presynaptic cell and a postsynaptic cell. And the information that's flowing along this axon is an action potential, because action potentials flow along axons. And that electricity that flows along here will be converted to electricity that flows along here. But we already know that the electricity that flows along dendrites is not an action potential. It's a graded potential, right? So action potential is going to be converted to a graded potential here. Now the graded potential will probably fizzle out if we just have one graded potential. Like right here, it's going to fizzle out. It's not going to make it to this axon hillock. So here we have an incoming action potential, and don't forget, this is a little synapse here, and when this action potential comes to the end, it's going to release a neurotransmitter. And we're going to assume, since this is an excitatory, there's a little E there, E1, this is an excitatory postsynaptic potential, that this neurotransmitter that's being released It's an excitatory neurotransmitter, so it causes an excitatory postsynaptic potential to occur here. It depolarizes this membrane and causes that graded potential, which is classified as an EPSP. Graded potentials are either going to be IPSPs or EPSPs. In this case, we depolarize the membrane, and that wave of depolarization is going to try to travel to this axon hillock because we want an action potential to keep on going, right? So that neurotransmitter is released, and it excites this little dendrite here to create a graded potential. It opens up sodium-potassium gates to allow sodium to go in and potassium to go out, and it creates a wave of depolarization, in this case a little graded potential. And this graded potential start to go along. But here on this graph we see that this graded potential wasn't big enough when it reached the axon hillock to create an action potential. So it wasn't big enough. And so then, at a second time, another action potential came along and did it again. So we had action potential, graded potential fizzled out. Action potential, graded potential fizzled out. So there was no summation here. But here in our second example, instead of, oh, I hate it when that happens. Sorry. Recording too many lectures at once. Here, in our second example, we didn't allow that much time to go by. Here we sped up the stimulus. We had an action potential that went through, and that action potential was going, and and it created a graded potential, and another action potential came by quickly enough to where another graded potential came through, and so graded potential and another stimulus came through. So the second graded potential, when the graded potential came through, another graded potential came through, and both of those together were enough to reach this axon hillock to create an action potential. So we had temporal summation. This was over time. So two graded potentials added together to create this action potential. Now you can't add the graded potentials here, but it's just that one graded potential wasn't enough to reach it, but two graded potentials could reach this axon hillock to create an action potential here to go on. I always like to think of it as kids pestering me because they'll wear you out over time. So if they ask you once what's for dinner, you could ignore them. They ask you twice what's for dinner, you could ignore them. They ask you 3 times what's for dinner, you could ignore them. But the third time you're like, we're going out to eat, So you can just wear you out over time. 1, 2, 3, they finally make it. So temporal summation is over time. Now spatial summation is coming in from over space. So here we have one action potential coming in. We're going to get a graded potential created. Now if we just had graded potential coming in this way, it wouldn't make it. But if we have a graded potential coming in here and a graded potential here, both of those at the same time can make it to the axon hillock, so an action potential can be created. So that's over space being added together. Again, if you want to do the kid thing, one kid pulling on one arm might not bother you, but 2 kids pulling, that'll bother you enough to be aggravated enough to create an action potential. Now we can summate our IPSPs and EPSPs. Here's this guy is exciting and this guy is inhibiting. So those guys will wipe each other out. One excites, one inhibits, and the neuron has to keep track of all this stuff. So we can summate over time, and we can summate over space. Those are our EPSPs and our IPSPs. And that all has to do with you keep a track of who's the presynaptic cell and who's the postsynaptic cell. Now these are all presynaptic cells here, and this is just getting into more detail on naming synapses of these presynaptic and postsynaptic cells. If an axon comes into the body, we can call it an axosomatic synapse. If an axon comes into a dendrite, we can call it an axodendritic synapse. If an axon comes straight into an axon, it's called an axonic synapse. In this case, we would have an action potential that always would create an action potential because action potentials can always create action potentials. There'd be no um, graded potential trying to get to create an action potential. This is 100% going to create an action potential. Now, there are other types of synapses, other ways to classify synapses besides the way we just did. Uh, Chemical synapses are the majority of our synapses because this is when a neurotransmitter is released by one cell and it docks on another cell. But we have another type that's quite rare in adults. They're only in certain brain regions, like our hippocampal region for learning, and there are some other places in our brains for stereotypical movements like breathing and arm waving, where we have electrical synapses. In these places, we have electrical coupling of our neurons that results from gap junctions, where we have two neurons that instead of having a synapse where there's an actual space between the two cells, the cells are connected by gap junctions. And then that way, there's absolutely no synaptic delay between cells. The cells talk immediately with one another. And then that way there's immediate communication. These are very rare, like I said, compared to the chemical synapses, which are all over the body. These are much more common when we're embryos, and then they convert over to chemical synapses. So electrical synapses rare, not so rare in embryos. They're very common in embryos, and then they convert over to chemical synapses. Okay, we'll talk about neurotransmitters next time.